All right, let's get started this morning. Good morning and welcome to the first Illinois EPA Office of Energy Wastewater Treatment Plant Energy Assessment Program webinar in a three-part fall series this fall focused on operations and maintenance for energy efficiency. Today's webinar is titled Lift Stations, Best Maintenance and Practices and Upgrades. My name is Cassie Carroll. I'm the Marketing and Outreach Program Manager here at CDAC, the Smart Energy Design Assistance Center. And I, along with my team members, are excited to chat with you today about common opportunities we see for lift stations in the Wastewater Energy Assessment Program. Everyone has lift stations, and there are some great ways to maintain them and in a way that saves both energy and money. A few quick housekeeping items before we get started today. We will be recording today's session, and we'll share the PowerPoint slides with the recording after the session has concluded. We will have time at the end of our session for questions as well. We'll have a couple of additional CDAC team members join us, and will share their insight and help answer your questions. If you have a question, please find the Q&A button at the bottom of your screen. Feel free to type in your questions as they emerge, and we'll address them at the end of our session. We'll also have, we've also enabled the chat feature, as you have seen here. We've got some great chatters already, but please feel free to use that as well as a great way to communicate with us. And also, I'll be dropping some items in the chat throughout the session, so please check it periodically for various information. Finally, CEUs and PDH certificates will be available after the session is concluded. We will be getting a course number as well from IEPA for operators. But if you're interested in CEUs or professional development hours, certificates, or course information, please email me at cassie@cdac.org. I will also drop my email into the chat when our engineers start speaking, so that information will be there as well. Okay, let's dive in. I'd like to talk to CDAC, or talk about CDAC really quickly before we get started. So we're an organization that helps buildings and communities in achieving energy efficiency, saving money, and becoming more sustainable. So we're actually, Smart Energy Design Assistance Center is a applied research program at the University of Illinois. And we have a private partner in Chicago, 360 Energy Group, but really we're here to reduce the energy footprint of Illinois. So that's why we work with the wastewater treatment industry and systems to help you save energy and reduce your energy footprint. Part of what we do is we work with the Illinois EPA Office of Energy to provide no-cost energy assessments to wastewater treatment systems. This effort is funded by the Illinois EPA Office of Energy in partnership with the U.S. Department of Energy Sustainable Water Infrastructure of the Future, or SWIFT Accelerator. We do have another partner, the Illinois Sustainable Technology Center at the University of Illinois, that also performs assessments with us in partnership for this program. Through an energy assessment, we can explore a variety of different aspects of your system for energy efficiency opportunities. Through our assessments, we provide a detailed cost of upgrades, estimated payback period, any funding and incentives that are available for your wastewater system. So if you're interested in having us come out after this session and uncover opportunities for energy savings across your wastewater processes and systems, you can register for an assessment at cdac.org/wastewater, and that's at the bottom of this slide right here, or you can just email me. You have my email address as well, and I'd be happy to help you get connected. So without further ado, let's dive into the content for today's session. We have two esteemed energy engineers from our CDAC team that are going to be presenting today. We have Hannah Ahn and Jane McClintock. But first, Hannah Ahn will kick us off in starting to talk about lift stations today. So Hannah, please feel free to take it from here.
Thanks, Cassie. So throughout this program, we've assessed many wastewater treatment plants throughout the state. There's a lot of focus on keeping the main system running and addressing issues there that oftentimes lift stations don't quite receive the same amount of attention or budget. On this slide, we've listed some of the issues we frequently encountered at lift stations. One of those issues is oversized pumps. So it's important that the pump capacity matches the quantity and quality of wastewater being treated. Other common issues include pipe clogs and equipment failure. It's important for lift stations to operate reliably. The next one is limited space for future expansion. This tends to be more common among older plants where the system may have been designed appropriately for the size of the community at that time, but in recent years, the community may have increased to the point where the system can accommodate the expansion. We've also encountered overflow and flooding as well as excessive odors. So during today's webinar, we'll be talking about how to address some of these issues. But before we dive into maintenance and upgrades, we'll spend some time reviewing some basics. I'm sure many of you are probably familiar with these, but we just want to make sure we're all on the same page. There are two basic variables to describe pump behavior. One is capacity, which is the flow rate of the pump measured in gallons per minute, and the other is head, which is energy supplied to the wastewater per unit weight, and this is measured in feet of water. On our graph, you can see we have our capacity, our flow rate along the x-axis, and head pressure along the y-axis. These two factors make up the foundation of pump and system curves, which we'll discuss shortly. Next slide, please. So on this slide, you can see two red dots on our graph. The dot on the left at about 55 feet represents the pump's pressure capacity. We know this because the flow rate is 0 at this point. And on the reverse side of that, we can also see what happens when the pump's pressure is down to 0. Then the flow rate is at its maximum, which is about 27 gallons per minute on this graph. So essentially, these two dots represent the limits of the pumps. What a pump curve allows us to do is understand how a pump operates between these two states. So we can't just draw a straight line between the two and assume that's how the pump operates at different states. Next slide, please. A pump curve is a representation of a pump's performance over varying conditions. It helps you choose the right pump for your system. Each pump has a different curve based on pump horsepower and impeller size and shape. For lift stations in particular, the pumps must be designed to overcome the head required to deliver the wastewater to the treatment facility while providing the minimum amount of flow necessary to prevent overflow at all possible flow rates. Next slide, please. Here we'll go through an example of how to select a pump for a lift station. For this example, we have a lift station that must overcome 40 feet of head and move 500 gallons per minute during high flow events. So in order to find a pump for this lift station, we go to our graph on the right. The dashed lines represent different pump sizes. So we have 3 different pump sizes on this graph. We have 5 horsepower, 7.5 horsepower, and 10 horsepower. The solid lines represent impeller sizes. So we have 2 impellers here. We have 10.12 inches and 11 inches. And then we also have, sorry, could you go back? Thank you. And we also have these parabolic lines, and those are lines of efficiency. So first we need to find our operating point, which is the point of 40 feet of head and 500 gallons per minute. So the point would be at that corner of the 2 yellow lines. So we can see that it meets with the pump curve for the 7.5 horsepower line. So this is the pump size we want to go with. And then this block where with the yellow highlight, everything in this block represents the amount of energy required to generate our specified flow and specified head. So selecting a 5 horsepower pump would give us an undersized pump, while selecting a 10 horsepower pump would give us an oversized pump. Then we'd go back to our efficiency curves. And so for an 11-inch impeller, the pump would operate at about 65% efficiency. When selecting a pump, while it's important to consider high flow events, we should also account for our most frequent flows, because that's the state the pump will be operating at most of the time. So we want to find the best balance for our system. Next, we'll move on to system curves. A system curve shows the relationship between the required inlet pressure to produce a certain flow. As the applied pressure increases, you can see how the flow rate increases as well. The slope of the curve indicates whether the system is friction dominated, which is indicated by a steep slope, or if the system is controlled by static pressure, which is indicated by a relatively flat slope. Combining the pump curves with the system curves allows us to understand the performance of the lift station over a variety of conditions and to identify opportunities for savings. The graph to the right here allows us to visualize these savings. So in this case, the savings are being generated from adding a VFD, and Jane will talk more about this later on, but I just want to point out those blocks that we just talked about for representing the energy required. So our initial case is the tan block. And then we have this smaller case or smaller block with the blue block, and you can see that tan area represents our energy savings. So the amount of energy savings from a 25% head reduction and a 20% flow reduction. There are generally two different types of lift stations that we see, dry well and wet well. So dry well lift stations are actually a combination of dry well and wet well areas. Because of the separation of dry well and wet well areas, they do require more space. However, the benefits to having the pumps and systems housed separately are that it makes it easier to access and maintain, and they're generally more energy efficient. In a wet well lift station, there's a submersible pump that is located directly in the wet well. It's usually less expensive since you're working with a smaller footprint. And since it's a more simplified system than a dry well, it's easier to install. Next, we'll be talking about lift station maintenance and the impacts on energy. Monitoring pump run hours is a fairly common practice we see at plants, a daily log of the run hours. It provides operators with a baseline to help track, target, and identify issues, whether it's I&I or repair work that may need to be done. It gives us the ability to track trends over the time as well, seeing if there's an increase in flow when more users are added, and if so, by how much. It can also help identify cases where short cycling or abnormally long run times are occurring, which are opportunities for savings. So short cycling refers to cases where pumps are turning on and off very frequently. If your pumps are short cycling, this indicates that they're not operating at their highest efficiency. One potential solution to this is to fine-tune the height of the floats at your lift station so that the pumps have longer and more infrequent run hours. Not only will this reduce energy, but it will also reduce wear and tear on the pumps from constantly turning on and off. On the other hand, you may be encountering abnormally long run times at your lift station. One factor that may be contributing to this are clogs in the check valve. If debris is keeping the valve from closing, water will flow back down to the pump and cause excessive recirculation. This will significantly increase run times. If left unaddressed, this will also cause wear and tear on the pumps and increase energy usage and costs. Next, I'll turn it over to Jane to talk about pipe cleaning.
Thanks, Hannah, and thanks everyone for joining us. We're excited to have the conversation today. Another factor that can lead to long runtime hours but can sneak up on you is clogs in the pipes that run to the water treatment facility. So these can build up over time and effectively increase the static pressure and friction head in the system. So one way to assess this is to have a pressure sensor on the line, which can provide a baseline pressure and allow you to see whether you have any gradual increases over time that need to be addressed. Also, if you see a sudden decrease in pressure, that could alert you to a line break. Alternatively, if you don't have a pressure sensor, but you have a means to measure flow, you could check your pump curve for your pump and the system design head pressure, and see whether the number of hours you're logging for that pump makes sense with the system. And if the runtime hours are excessively long, you may want to look for a clog. And one way to address that, if you find that you have a problem with abnormally high pressure in your lines, you can turn to progressive poly pigging, which is often more commonly referred to as pigging the lines, where a series of pigs, these polycarbonate, and they come in many different forms for different problems and different sizes. A series of larger and larger pigs are forced down the line. In this case, in the picture here on the right, they're using the fire hydrant to use the water pressure to force down the line. And this process, if there's, especially if it's really, causing excessively long pump times, this can have immediate benefit the first year in terms of payback in energy savings. And another thing that can sneak up on you and be a kind of quiet energy hog is clogs, partial clogs in the impeller. Of course, it's obvious if there's a complete clog in the impeller, and it becomes a maintenance emergency. But it's been observed that impeller clogging, partial clogging, can be a real energy hog. Flight pumps, in their laboratory testing and also their field validation, have found that that conventional pumps that ran intermittently had as much as 20 to 30% reduction in their published efficiency because of clogs. And for pumps that ran continuously, so they didn't have an opportunity to break up those clogs when they started and stopped, the efficiency losses were even more dramatic. So in their estimation, the importance of delivering sustained efficiency through a self-cleaning impeller, a clog reducing impeller, was 10 times more than specifying a high efficiency motor, which could only be 2 to 3% more efficient than a conventional one. So this is something to think about later when we are thinking about, there may be some energy impacts to keeping the lift stations from clogging, but the sustained efficiency that that the pumps experience could pay off for those bits of loss of efficiency due to the self-cleaning impellers. And furthermore, we're really underscoring the energy importance of this kind of proactive maintenance. But of course, I'm sure you all know that there's also other benefits to proactive maintenance, such as the peace of mind of not hearing about your lift stations or thinking about them on Friday night. So from here, we want to move on from maintenance to some of the improvements and enhancements that we see benefiting lift stations in terms of energy. And one of those most frequent ones, and the one people think about the most, probably are variable frequency drives. And this is with good reason, because these can be a really beneficial investment for lift stations because they're able to modulate the pump speed to the demand. And of course, as Hannah had pointed out to us, lift stations are a particularly interesting case because the different run times can change. So at high flow events, you might need a pretty large pump, but most of the time, you're actually designing for, smaller flow. So the variable frequency drives can be a good investment, and their incentives are available. So Ameren, Illinois, $125 per horsepower, up to 80% of the cost of the project, and ComEd, 12 cents or 21 cents for plants that have DO. So some of those projects might even get a little more incentive than what's here. And then the reason that VFDs are such a great investment is, you guys are probably familiar with this, but I just wanted to underscore it, that the amount of the relationship between the flow and the speed is linear, but the relationship between speed and energy consumption is to the third power. So we're only reducing the flow in a linear way, but we're saving energy in an exponential way. So this can provide disproportionate savings. And this holds true also for a smaller impeller size. So impeller diameter has the same affinity relationship to energy savings. But when we're talking about a retrofit scenario, this can be, there's an efficiency drop to just trimming the impeller. So we usually talk more about VFDs, and also because they have this ability to meet those high flow demand periods and ramp it back. And so next, we want to talk about some added benefits, which are reducing wear and tear on the pump. And then we talked about problems with clogging impellers. And one of the things that some VFD setups can do is run the pump in reverse for a little bit to start breaking up some of those clogs. So this could not only enhance the ongoing efficiency of how the pump runs, but also provide those VFD incentive, the energy savings we talked about earlier. And one thing we see is throttled pumps. So where there are pumps that are oversized, sometimes folks throttle either before the pump or after the pump to reduce flow. And as we can see here, the throttling does have some energy efficiency benefits, because you're essentially taking that system curve and bending it up a little bit by adding to the static head, creating a little bit more pressure on the system, which decreases the flow. And so there's some energy savings there, but on the left, you can see that the VFD provides substantially more energy savings, and also, again, provides that ability to meet those high flow periods when it's needed. And yeah, and then this is a familiar graph here where we see the system curve in relationship to the way that a VFD is able to ramp down the speed of the pump. And I wanted to show this again so that we could think about times that VFDs might be a good fit for a lift station. You can see that this is probably a pretty average system curve for a lift station, but maybe with a little bit of high static head. So you really only turn down before you're getting to that intersection with the low flow operation to 85%, and that's probably kind of pushing it. But if you had a much steeper system curve, like imagine that the system curve was more like the best efficiency point curve, then we could see that the system was much more friction dominated, there was less static head, and we'd be able to turn the speed down more and still be able to overcome the static head in the system. So that the steeper that curve is, the better fit it's going to be for a VFD. Also, you've got to see some amount of variable flow for a VFD to be a good investment, because if the pump isn't going to have the opportunity to turn down because it needs high flow all the time, then a VFD maybe won't have as much savings. The other opportunity to think about VFDs is when you're replacing your pumps, because you may be able to consider a package smart pump, which has a VFD installed from the manufacturer, which provides a little bit less engineering on site to do a retrofit, and also it's designed to work with that pump. It's already commissioned together from the factory. So these can be a really great VFD setup. And then, of course, you're going to want to be looking at pumps that are using enough energy to potentially have savings to pay back the investment of the VFD. So I would think 10 horsepower at moderate run hours per year is when I start to think about VFDs at lift stations. But if you have more flow, then even a smaller pump might be a good candidate. And next, a possibility when a VFD isn't a good fit and when you still need to meet high flow times, and so you can't just simply trim an impeller or step down the size of a pump, is to possibly add another smaller pump to run during moderate flow times. So adding yet another float and pump that work when you don't need those high flow periods, and let your larger pumps, which of course you still need to maintain redundancy with, let them take care of those high flow times, but only when needed. Other upgrades are we talked about partial clogging of the impellers and some of the energy impacts there. There are different kinds of solid handling non-clog pumps. So if you're looking at replacing pumps, you might consider different kinds of Impellers. There are a couple different kinds of non-clog impellers here shown in a Bell and Gossett pump, the BFK model and BFV. The one on the right, the BFV, has a vortex impeller. You can see that the solids would actually rarely even come into contact with that impeller. It uses a suction kind of action to pull the material through the pump without actually coming into direct contact with it. So this is a very clog resistant system, but it's a little less efficient. But again, you know, that efficiency, it depends on your lift station. If you're having really, you know, quite a lot of problems with clogs, if, you know, it's maybe you have some problem users that, you know, are I don't know what, you know, if it is a repeated problem, then maybe it would be worth the efficiency impact of the vortex impeller. There's also, as you can see on the right, semi-open impellers that pump manufacturers have designed to be efficient, a little bit more conventional efficiency, but have a design for non-clog. So if you are just having more moderate problems with clogging, this might be a good system. And then for areas that a non-clog pump is not enough, our next slide is about grinders, screening. So this is sort of the next step up. And of course, that grinders and choppers, augers, screens, they're going to have an energy impact in the sense that you're adding equipment that's going to have its own horsepower requirements. But these are going to be able to cut up that fibrous material that is causing problems in the pumps, or in the case of screens and augers, just take it out. A grinder pump is where a grinder is integrated in the pump. A conditioning chopper pump is kind of the immersion blender of the lift station. This can be portable even and moved from multiple lift stations. So if you're finding that you're very frequently having to pump solids out of your lift stations, then investing in a conditioning chopper pump might make sense for your wastewater system. An inline grinder is like shown at the upper left there. It's something that can take care of solids as it enters the lift station, and it can fit in a variety of applications. And finally, screens and augers can actually pull the solids out before they even get to your plant. So this can have some benefits, you know, both for the lift station and potentially for the process down the line. And then, yeah, with that, I will pass it back to Hannah. Thank you so much.
Thanks, Jane. So lift stations are often accompanied by odors, particularly hydrogen sulfide, which gives that rotten egg smell. When hydrogen sulfide, also known as H2S, oxidizes with aerobic bacteria, sulfuric acid is produced and leads to the corrosion of metal fixtures and pipes, as well as concrete. So you can see an example of this in the picture here. It can negatively impact workers' health as well. Operators may experience symptoms such as headaches, skin and eye irritation, sore throat, loss of consciousness, and other health problems. It can also impact relations with your community, which I'm sure everyone here would like to avoid. It's important to address since replacement of corroded equipment and infrastructure is both cost-intensive and energy-intensive. There are several ways to reduce H2S. One reduction strategy is oxidation through the addition of chemical oxidants, such as hydrogen peroxide or chlorine. Another is precipitation of dissolved sulfide through the addition of metallic salts, such as chloride or ferrous sulfate. The dissolved sulfide is converted to an insoluble precipitate, which prevents the release of H2S gas. The third strategy is to increase the pH level through the addition of sodium hydroxide. And the graph to the left displays how the amount of hydrogen sulfide varies over different pH levels. So you can see at a pH of 6.0, you have over 90% H2S, and then at higher pH levels, smaller percent of hydrogen sulfide. There are also protective coatings available on the market to help with corrosion control. So these are all options you may want to consider, as reducing H2S can help extend the useful life of lift station components and infrastructure. At some plants, you might send someone out to a lift station to do a weekly inspection, make sure things are running. But between these inspections, anything could go wrong. So we at CDAC encourage plants to implement a remote monitoring system. Otherwise, a problem at the lift station could arise and it could go undetected until the next time someone is out there. So we've seen varying types of controls and equipment and data collection at lift stations. Here we compiled a short list of some of the more common controls that you may want to consider incorporating at your lift station if you don't already. So just having the ability to monitor the current status of the lift station remotely, whether it's from your office or from your home, instead of having to go out to the lift station, can not only help you save energy, but also just give you a peace of mind, as Jane mentioned earlier. A remote monitoring system also gives you the ability to control components manually or program a lockout. Level sensors and switches help control, manage, and monitor liquids. They are helpful in ensuring the proper treatment of wastewater. A runtime meter can help with automatic data logging and generating pump runtime reports and flow history. And having the system set up so that alarms are sent directly to your phone via email, text, or call. So for example, if a pump at the lift station fails, you can have alarms go off and alerts sent to your phone so that you or one of your other operators can go out there and address it as quickly as possible to help prevent any further issues from happening, or again, dealing with any potential outcry from the community. And if you're interested in learning more about data technologies at wastewater treatment plants, we have a webinar on optimizing wastewater treatment plant operations through data and analysis technologies that will take place on November 17th at 11 a.m. I believe Cassie will be dropping the link to register in the chat box. If you're interested, please follow the link and register so that it's on your calendar. And that concludes our presentation for today. So now we'll open it up to questions. For this portion, we'll have Robert Nemeth, our technical director, joining us, as well as Sean Maurer, one of our senior energy engineers. Thank you.
Thank you so much, Hannah and Jane, for an awesome presentation. So much good information throughout the entire session. Just a reminder, if you do have questions, or even if you have tips or things that you do at your wastewater system to manage your lift stations, or things that you found to be really useful, feel free to drop those in the chat too. We'll share them across our webinar as well. Also, again, my email is listed at the top of this slide. Again, if you're interested in those CEUs or professional development hour certificates, just drop me an email, let me know. Great, we have a couple of questions already in the queue for our panelists. So thank you, Robert and Sean, for joining us. And these are the folks, if you do sign up for an energy assessment through the Illinois EPA Wastewater Treatment Plant Energy Assessment Program, you'll be interfacing with some of these folks, so you'll get a preview of working with our team. But our first question is there a process to determine normal running efficiency on pumps in regards to impellers? And any of the panelists can take this one to start us off.
Well, I could comment a little bit to that, in the sense that what Hannah was speaking to about the pump curve can give you a starting point. If you have, I mean, it would be great if you have the original designs for your system. So the design pressure and system curve is available to you, but you can also estimate what kind of a head pressure you expect on the line based on the elevation change in distance from your lift station to the plant, or to, you know, the next lift station. And once you know that pressure point and you have the pump model number, you can look up the pump curve. So bringing those two together, you can start to estimate and look at what kind of expected flow you should have from that impeller. I don't know if anyone has anything to add to that.
Yeah,
No, I think that's a good answer.
It's a great question.
Yeah. Mm-hmm.
Almost always going back to somewhere you should have manufacturer documentation on what your pump curves are, comparing those pump curves to what your actual flow rates and measured head pressures are. And from there you can plot it on there what your system curve looks like and where that's crossing your pump curve, and that'll tell you what your pumping efficiency is.
This is something that, you know, we're able to look at a little bit during the energy assessment by looking at runtime hours and the pump curves. But, you know, sometimes all that data isn't available. So, you know, about the original design of the plant. So sometimes some of that has to be recreated, like Sean's referring to.
Very interesting. Thank you for that response. We have another question in the chat. Do you see lift station pump applications being dominated by static pressure, thus VFDs having a limited impact on energy savings?
So we see a mix out in the field. Usually we're seeing lift stations lifting somewhere between 30 or 40 feet for, you know, average lift station. There are some that are higher, some that are less. And that is usually a significant portion of the overall head profile for their system curve. But usually the pumps that are installed are high head pumps. And so they have the ability to maintain a controllable range of head pressure on their system curve when you slow them down. You're not able to slow them down as much as you would, say, an HVAC pump or chilled water pump, which are typically dominated by friction loads. But you can usually back them off in the range of 50 to 60% if you've got a pump that's properly designed for that higher head application.
Thank you, Sean. Does anybody else have anything to add? Okay. We'll go to our next question here. Thank you, Sean. Are there funding opportunities available to help pay for the upgrades that you mentioned at lift stations?
Well, there's the funding opportunities for the VFDs, but some of the maintenance additions are a little bit harder to quantify in terms of kilowatt hours saved, so it can be a little harder to incentivize those. For instance, adding a chopper pump may well save a lot of kilowatt hours by reducing the runtime of your pumps, but that might be a little bit harder to quantify the savings because it's not direct. I don't know if Sean and Robert might have, maybe, and Hannah have more experience to speak to that.
Yeah, that's specifically speaking towards the utility programs incentives, but there are other programs as well. EPA's got their notice of funding opportunity that goes out for plant upgrades, which can include lift stations. There are a number of other programs as well. A lot of smaller plants can qualify for USDA grants, small rural communities. There's assistance from the, if I can remember what RCAP stands for, Rural Community Assistance Partnership. So there's a lot of funding opportunities out there. When we do an assessment, we try to detail those in our assessment reports, let you know which ones you're compatible with. Usually we'll only quantify the utility savings because those are fixed incentives. And other funding opportunities are usually competitively based and at variable amounts. So.
Yeah, just to...
Go ahead, Hannah.
I was just going to say, just to add on to that, as like Sean mentioned, just to build a little bit on that, some of the opportunities are, you know, could be on a rolling basis, first come, first serve, or just open for a certain period of time. So at the time of we issue the report, there is a whole section in there on the different incentives and program funding opportunities available at that time.
Thank you, Hannah. And I am going to pop in the chat. Sean mentioned the Illinois EPA Office of Energy's Wastewater Treatment Plant Energy Efficiency Grant. So there will be another round of funding coming out late fall, early winter, but the NOFO from last year is on there. So if you want to get an idea of the requirements or what kinds of forms that need to be filled out, I'm going to pop that in the chat too, because that's a great opportunity for funding as well. Does anybody else on our team have anything to add on this question? Okay. Well, we have another burning question in our chat box. Have you noticed more clogs with the use of VFDs running at lower speeds? We've recently upgraded to VFDs and we seem to be noticing more clogs and more time spent pulling pumps to remove clogs. I feel because they're running around 40 hertz for a long time and not pumping rags through a higher velocity as they would at 60 hertz. Does anybody have any comments in response to that question? Really, the question is, have you noticed more clogs with the use of VFDs running at lower speeds?
I have run across plants that have had settling issues in their piping from lower flow velocities. You know, their collection system was designed for higher water consumption back when we had higher flush per gallon toilets and faucet aerators and things. And as we've done water conservation, flow rates have decreased and that's caused settling issues. As far as VFDs causing more clogging, ragging issues, I haven't particularly run across that. I have run across that, you know, that VFD does have a backflow. I can run that pump in reverse to push rags out of it and then run forward, usually at full speed for an intermittent period and then backing down to draw through any debris that's in that container. So it depends on your VFD application, I think. If it's continuously running at low speed, I would see that could potentially cause issues. But a lot of systems are designed with anti-clog features now that try to prevent that.
Yeah, I wouldn't doubt that at all, that you're experiencing increased clogging with lower frequency. You just don't have the energy that you're inputting typically when that motor is running full bore to push that rag on through. But like Sean said, with the new technology, some of those do reverse automatically when they sense that impediment and to try to clear that clog.
Awesome. Are there, oops, go ahead, Jane.
I have read, but not seen, that some of the slow starts on the VFDs, the slow ramping up, can decrease some of the natural flush out that happens when the pump starts. So again, adding an additional feature that will either run it in reverse or make sure that it's not, the slow start is not creating a clog problem. I think I've seen some products too that will create a jet to kind of blow out the pump so that when it starts at slower speed, it can clear the impeller. So some of that might help out with the VFD slow speeds.
Well, it looks like we have one of our team members on the call, but he is somewhat incognito as an attendee, but he has something that he wants to add to the conversation. So introducing Ryan Siegel, also a member of our CDEC team, to provide some commentary as well. Ryan?
Yeah, well, thank you, Cassie. Something that we have also come across as far as how to...
Whoops, I think we might have lost him. Oh no! Ryan, are you back, Ryan?
There we go.
All right, well, he's back on.
So something else that we have found sites that have done to address this is when a pump starts with a VFD, to go ahead and bring it on full speed for the start of its cycle, and then slow down once the flow has been established. So that's one method. Another method we have seen for addressing clogging issues with VFDs. Because yeah, as mentioned before, if you just get a slow start on it, that can lead to some clogging issues.
Awesome. And then I see somebody made a comment in the Q&A as well. Program to start at 100%, then go to VFD regulating as well. Awesome. Thank you. Thank you for adding that context, Ryan. Ryan also is one of our energy engineers, senior energy engineer that works in the wastewater treatment program as well. Has anybody else, I know it looks like I've been getting some chats and comments that this is a common problem. I hope that these provide some good ideas for solutions for you as well to mitigate that issue.
I've also read a couple of articles and heard from a few people that with COVID, the uptick in cleaning surfaces and things with sanitation wipes, that's caused a lot more clogging issues because all those wipes getting flushed down the drain.
Definitely.
Yeah, it's a major problem. I think probably the best way to address that with rags and stuff, a chopper pump usually can handle solids pretty well, but rag type materials tend to wrap around those still. They don't get cut up as well. Probably the best way is to strain those out somehow and remove them before they can get to your pumps, if at all possible.
Definitely. All right. Well, thank you for all that good conversation around that topic. It seems to be really pressing with our audience today. So thanks for those good tips. And if you have any other tips, again, pop them in the chat or things that you do or the Q&A section, and we'll share that live in this Q&A session here. I have another question too from our attendees today. I know that energy use varies on number of lift stations and size of your plant, but on average, is there a percentage of energy that's directly used by lift stations in a wastewater system, or does it really depend on conditions?
It's really going to depend on the design of your infrastructure. Do you have numerous lift stations, and do they represent a serious load or portion of your load from the wastewater treatment entity, or do you just have one or two lift stations and most of your power is being consumed at the plant? So it really, that's going to vary a lot from context to depend on context.
Okay.
Yeah, for instance, in a lagoon system, the lift stations are a bigger percentage of the overall energy used at the plant compared to an activated sludge. And sometimes, this is kind of part of why we wanted to bring this up, is that a lot of times when we are talking to the operators about doing the assessments, and they're a little hesitant to maybe get into providing data or thinking about the lift stations because they are a relatively small portion compared to the big users, the blowers and things at big plants. But we wanted to remind everyone that even if they're not the biggest wedge of the pie in your plant, they're still quietly using energy. And so, some of these lift stations, if we can get on top of maintenance, we can still make some pretty substantial improvements in energy use. And they may not be the biggest, but they're still there and they're important. And for the maintenance reasons that they won't cause you less headache.
Awesome.
That's a great question.
Just kind of scanning quickly through some of the typical energy breakdowns, from EPA and other sources, anywhere between 10 to 20% can be pumping energy. And that's going to include the lift stations that are out in your distribution network as well. And as Jane mentioned, certain facilities such as lagoons will have a higher percentage of that pumping energy. Facilities that haven't made optimal use of gravitational flows, that pumping energy is going to be a higher percentage, as well as you'll have intermittent or kind of interstitial pumping lift stations within the plant as well. Yeah,
Awesome.
It can be a big chunk, and even if it's not a huge energy component, it is a large maintenance component So if there are ways you can reduce the maintenance load on those, that's also a cost savings.
Awesome. Thank you for those comments, and thank you to Thomas from the City of Heron for that kind comment as well about VFDs and remote monitoring. So we're excited that you found some great benefit from the assessment and the work that we've been able to help support you in doing. So thank you. We have another question. How does I&I impact lift station operation? How does also oversizing pumps to handle I&I impact at the energy consumption of the rest of the year affect that? Does anybody want to take that
Sean,
question?
you want to comment
Let's
on
say
that?
I can jump on that right away.
Yeah.
I've been working on our I&I study. I wanted to see if
ahead.
anyone else wanted to take it first.
No.
Go ahead, Sean.
So certainly upsizing pumps to handle I&I flows. Typically, those storm flows are a small percentage of the year. So when you oversize the pump to handle that high flow, and then especially if you don't have a VFD, the pump quickly draws down your wet well and then shuts off. You've got a lot of rapid on and off cycling of those pumps. That's a lot of wear and tear on that motor. The rapid drawdown too can also, it allows buildup of materials in that wet well. Because a lot of wet wells, you're not going to draw down that fluid flow until you're sucking, floating surface debris in. When you add a VFD onto that system, especially if they're heavily oversized, a lot of the times you're probably going to run into some of the situations you've run across where you've got, the pumps are running at 40–50% speed, and now you've got clogging issues because you're not sending debris through that pump at high velocity like you were with a full speed pump. And so designing a pump to handle those I&I flows without first trying to address that I&I and reduce how much oversizing you need to handle those high flows can have a huge impact on energy and maintenance for those systems. But another nice thing about pumps, if you can track the run hours and things, it does give you a handy way to track down where I&I is in your system. You can look at which lift stations have higher run hours than others, and maybe that's where you got to target your I&I abatement plans.
Awesome. Thank you, Sean. Does anybody else on our team have anything else they'd like to add?
Just the only thing that the I&I, some plants have got I&I pretty well under control, others don't. That is a lot of water that you are not only having to pump from the lift station to the wastewater treatment plant, but have to treat too. So, you're paying quite a penalty for high I&I rates.
And that's something also as a part of our assessments that we can take a look at too with you. If that I&I is an issue, that's something we can do some evaluation on as well for you. So just wanted to note that as well. Thank you for that question. All right. I don't see any more burning questions in our Q&A box or in our chat. So I'll just pose one question to all of our panelists. Is there anything that we might have missed today or anything that you'd like to add before we wrap up today's session?
See one question come in about the Ameren VFD incentives here.
Oh, okay.
It says, if you get the Ameren incentive for VFD upgrades, do you have to meet certain energy consumption reduction, or are you able to run the VFD program how you want?
Thank you, Sean.
Yeah, just saw that pop in. Jane, you had talked a little bit about the programs you want to.
Oh, sure. Yeah. The Ameren program is a fixed amount per horsepower. So if you have a 10 horsepower pump, it's going to be 10 times $125 will be the fixed incentive. But yeah, it will have to be pre-approved by Ameren. So you would, once you identified a lift station that you thought was a good candidate, you'd reach out to Ameren, and they'd send somebody out who would look at your project, see whether it made sense, whether they saw the same energy savings that you did, and then it will be that fixed incentive. Whereas the ComEd, as you saw, is per kilowatt hour of savings. So, and that ComEd incentive is actually, they'll verify those savings in operation. But that ComEd incentive can be up to 100% of the project cost.
Yeah, I know in the past, I'm not sure if the restriction is still there, you had to have a minimum runtime hours of 2,000 hours per year to qualify for incentives. And there has to be some savings potential. You can't have a pump that you put a VFD on it and 90% of the year it's running 100%. There has to be some energy savings potential. What the specific threshold is, I'm not certain.
And again, through those assessments that we perform, we can run some of those calculations for you and see how much your incentive might be. And as a part of our program, we help with implementation support too. So if you do need help with applying or figuring out how to apply for those incentives, we provide that support to you as well.
But tying that back to high head pumps and putting VFDs on those, I've run across, it was a water treatment plant, not a wastewater plant, but they had high head lift pumps for filling their water towers. And they still qualified for an incentive for the VFDs, even though they could only back off their pump speed by maybe 20–30% instead of 50–60%. But they're still getting 20% reduction in speed is somewhere around a 35% reduction in energy. So there were still savings there.
Awesome. Thank you. That was really great information. All right. Andrea Roy from Ameren Illinois Energy Savings Program said there's incentive for minimum operating hours of 2,000 hours per year, up to 80% of the total project cost. Cool. Thank you, Andrea.
Thank you.
All right. So we are nearing 2 minutes to the end of our session today. I'll pose my question to our panelists one last time. Anything else that you'd like to add before we wrap up today, or is there anything that we might have missed?
I think one case study we had a lagoon plant. We looked at a primary lift station coming into the plant, and the effluent coming out of the plant, when we calculated what was coming out of the lift station, was about half of what the lift station was pumping. Well, that's not possible, or the lagoon would be overflowing. So something was up there. So we were able to get that plant looking into whether there was a check valve problem, a pipe leak, a pump seal, something that was causing excessive recirculation there. And I haven't heard back yet whether that plant has found and addressed that issue. But it's potentially, half the energy consumption could be removed from that lift station.
Neat. Thank you for sharing that, Sean.
All just found by looking at effluent flow rates and influent flow rates to the plant and calculating from the run hours of the pump and what it was designed to pump at.
Awesome. Anything else? Anybody else want to add anything before we break today?
I just want to thank everyone for coming out and joining us and thinking about lift stations.
Awesome. Well, thank you to Hannah and Jane for leading our presentation today. Thank you to Sean, Robert, and Ryan from our team for joining us on the panel. This was a lot of fun. Great discussion today. Thank you for all of your questions and your insight that you shared today as well. Again, I will be sending out the recording of this session as well as the slides. And again, if you're interested in the CEUs, I'll send out the course information, but I'll also be sending certificates as well. So we thank you all for joining us today. We hope you can join us on our second webinar in this series on October 20th, phosphorus and nitrogen removal strategies. We look forward to seeing you again on an upcoming session, and I hope you all have a wonderful day. Thank you for joining us. Take care.